Hey everybody, welcome to this presentation. My name is Michael. Today we're going to talk about quantization in fine-tuning large language models with QLoRA. Now let's begin. So for the overview of this presentation, we're going to talk about the ideas of fine-tuning and what that is, the idea of quantization, how that works, and also a concept called LoRA, a low-rank adaptation, to really help us to fine-tune our large language models. Now let's begin. Fine-tuning. So the large language model came out. It's usually called a pre-trained model, and that is a model that kind of only predicts the next token. It kind of finishes the sentences where you left off, and it goes through a series of processes to become what we're known the chatbot style large language models today, like ChatGPT. Usually goes through a process of instruction fine-tuning, telling the models what to do, instructions and actions. And then, therefore, they go through some other fine-tuning process like safety fine-tuning, maybe preference fine-tuning, so that to make sure the model doesn't tell you how to break into the car or break the law, right? And then also and it goes through some other process if you want to further fine-tuning to maybe a specific domain, or maybe you wanted the model to perform a specific tasks, or you want to maybe really tune it to a specific user. Maybe an artist wanted to have large language models replicate his or her own art, so he can use his own data set or his own art as a fine-tuning data set. So there's a lot of ways you can really customize those models, but how does that work mathematically? So let's say we have a large language models and we have this pre-trained models, so they have pre-trained weights. So when we're actually fine-tuning, we're just adding additional weights, additional matrices of same dimensions on top of it, and therefore we get our final weights for our final fine-tuned model. It's basically addition of a added weights on the top of the original weights. It's really just simple as that. So now let's actually take a kind of a example here. Let's say if you want to fine tune a 7 billion parameter model, and this 7 billion is a really large model considering what Llama just came out with their 400 billion parameter model. So if we want to actually fine tune our hardware, it's actually pretty difficult. So we would actually load the model on our GPU. And if we have this quantized at 16-bit, which we'll talk about this in a little bit, then that will take about 14 gigabytes just to load the model on our GPU. And actually, for our average day user for our GPU, we don't have that much memories. Actually, 16 gigabyte is an overestimation. On my laptop, I only have 6 gigabyte of VRAM, so I can't even load that model on my GPU. Now, when we're actually fine tuning, there's different things we have to consider, right? There's gradient. The gradient has to be calculated with back propagation to go back and update those weights. You also will use optimizer like Atom or gradient descent, right? And then if we use Atom, there is another vector called momentum vector and also variance vector we have to calculate. That takes another 2 times the model size, and that takes 28 gigabyte. And there's some other things, activation, maybe large batches we have to calculate. So the memory footprint required for fine-tuning this model actually takes about 56 gigabytes of VRAMs. That's like 5 average computers, and probably even 10 if I use my own laptop. So it's impossible to actually do this on a single GPU. How do we deal with this problem? Quantization. So quantization is no more than just trying to find a better way to quantize our model, compress our model, so that we can do this more easily. So quantization, let's talk about this idea. So let's say, how does that work, right? Quantization. So if we have a range of numbers, let's say negative 200 to 200, and it's a continuous infinite number, so therefore to actually represent this number, it takes infinite amount of memories. The reason why is if it's truly continuous range of numbers from negative 200 and 200, and let's say they're normally distributed center around zero, so a lot of numbers are kind of jammed around zero. We can put unlimited amount of numbers in this distribution: 100, 101, 101.11, 101.11 to the infinite. So therefore, there's infinite amount of numbers we can use to represent this distribution, which takes infinite amount of memories. So how do we quantize this distribution? So we can only use finite amount of or discrete values to represent this distribution. So it's actually to quantize. Quantization is very much like histogram binning. So same idea. If we have a infinite range of numbers from negative 200 to 200, And I want to quantize this distribution into 256 amount of finite discrete numbers. Then I would use 256 different bins or buckets to put those numbers into those buckets. So essentially, I'm sliding this distribution through equally spaced with different bins and buckets. All the numbers that gets to bin into one bucket, then that all the number get mapped into the middle value of that bucket. Therefore, for this whole distribution, I only have to use 256 different discrete values to represent this distribution, right? So we've quantized this infinite range of numbers into only 256 amount of numbers. So that's where the magic is. Now, furthermore, I can even quantize this even more. I can quantize this into using only 16 different bins, and it's called the 4-bit quantization. We'll talk about in a little bit. 16 different bins, only 16 different buckets, and all the numbers get binned into one bucket, gets mapped to the middle value of the bucket. Therefore, I only need to use 16 numbers. But as you can see, the approximation or the estimation is not as accurate, or we lost some precision when we're jumping from 200 different buckets to 16 buckets. So there's some trade-off there we have to always be aware. So let's talk about this binary digits. So when we talk about 8-bit quantization, 4-bit quantization, what does that mean? So when we're using 8-bit quantization, there's 8 different binary digits. 8 different binary digits represent 256 unique combinations, which means there's 256 bins. That's why we used that example earlier. And if we want to use 4-bit quantization, we on the computer only recognize binary digits. So there's 4 different 0 and 1s represent 16 different unique combinations. That means there's only 16 buckets or bins we can use to put all the numbers into that one bucket. Therefore, there's less memory footprint that's introduced compared to 1 byte to 0.4 byte, which is four times less. So there's also this data type idea. We take data types for granted. There's integers, there's float points, but when we talk about different bits of data types, for example, in this 32-bit floating point number in IEEE 754, this is just a protocol everyone agrees to, so how to read those things. If we want to decode this number on the screen, there's 32 different bits of digits. So floating point actually means that the decimal point is floating. You can actually adjust this decimal point to the left, to the right, so that you always have a sign bit that shows you the positive and negative, and you also have exponent bit that can slide, because that's why it's called floating point, because it floats. And you have this called mantissa or fraction bit on the last side that represents the decimals. So if we want to decode this number on the screen into actual numbers, we take that kind of formula below there, the -1 to the sign, which is 0, which is 0. 1 plus the fraction is from 0.01 to decimal is 0.25. And times, because it's all binary, so it's 2 base, the exponent minus the bias. So for the 32-bit, the bias is always 127, so it's 0. So this whole number actually represents 1.25. So I just want to kind of showcase how those things kind of read here. And there's always all other data types you can use. For like neural networks, a lot of people use 32-bit or 16-bit, but you can quantize it down to like 8-bit, which we showed earlier. And so when NVIDIA come out with their H100 graphic cards, I think that's what they use. So that's why they can really perform really fast, because they can quantize it down. So it takes a lot less memory footprint. And if you want to go extreme, you can even do 4-bit. So 4-bit is always exists. When you see those exponent and fractions, you can kind of adjust this. So it's not fixed. It's not a fixed point number, but float point. So the decimal point can adjust. And the exponent can represent a lot more range. And also the fractions can represent a lot more precision. So it's kind of, you can customize it if you want to. So let's actually jump into this my cat here. So I have my 2 cats here. The image is on the left. I took it with my iPhone. So it's on a 24-bit integers. Now if I quantize this image into a 4-bit integers, a 4-bit quantization, we can see that the color is kind of degrading a little bit, because 4-bit integers only represent 16 different buckets, if we kind of remember what we said earlier. So 16 different colors can only be represented here. So the images on the right only have 16 different colors, but the images on the left is like so many numbers, right? So the kind of image is a little bit changed, but then we can see that the memory footprint from 2.44 megabytes to only 518 kilobytes. So there's a 5 times less memory footprint if we quantize it down. So therefore, we want to apply this idea to large language model. We want to quantize it down so we can fit them into our GPU. So therefore, if we quantize our 7 billion parameter model earlier from 16-bit to 4-bit, now it only takes about 3.5 gigabytes to load that model into our GPU. But when we're fine tuning, we don't want to quantize it because we're training, we're fine tuning. We want to have high precision. So those gradients and those optimized states doesn't change and other things. So totally that still use about 45.5 gigabyte. That takes about 3 kind of consumer grade computers, but we have quantized it down from 5 computers to 3 computers. So which is a lot of improvement. But I want to talk about this idea. So when we talk about quantizing, are we actually losing, are we degrading the model? Are we losing, we definitely lost some precisions if you saw the image I did earlier, but are we actually degrading the model? In this paper called QLoRA, it talks about this idea of how do we quantize our model, so compress our model, but not degrade our model. So it used a few ideas here, which is called, first one is flow point. They actually designed a new data type suitable for the neural network training. And it's basically a hard-coded binning strategy. If you want to go into more details, feel free to kind of research on. So it kind of helps the neural network more efficient, basically, with this new data type. A page optimizer is also mentioned in this paper. A page optimizer is basically loading a long sequence. You can offload the memories to the CPU, which can help like sudden spikes when you're training on the GPU. And also, we talk about this idea of double quantization. Double quantization is basically quantize twice. So when you quantize something, maybe higher bit into a lower bit, so there's a scalar value you also saved into maybe a 16-bit. So those scalar can also be quantized down. So therefore, you're saving approximately 3 gigabyte for a 65 billion parameter model. So there's a few techniques you can use to make sure that you are not losing performance. So when they use normal flow 4, which is their data type that they designed for this, and also they use the double quantization, you can see that by their 5 mean shot MMLU accuracy, which is just a evaluation metrics across different sizes of a billion parameter model, actually the performance is on par with the original state with the 16-bit. So it hasn't lost a lot of performance by using this technique. So which is something that's kind of a groundbreaking discovery in my opinion, so that you can use this technique to make sure you preserve the quality of your large language model, but not compress it, but not degrade it. So that's kind of important. So there are a few ideas also was mentioned, like blockwise quantization, k-means quantization, linear quantization. So for the purpose of this presentation, the scope of the presentation, we're not going into details into those concepts, but feel free to research on. So let's come back to the idea of fine-tuning. We talked about the fine-tuning basically adding a same kind of dimensional weights on top of the original weights, but we only talk about this pre-trained weights, right, on the left side. Is there anything we can do on the right side, under this orange side, anything we can do to make that smaller? The answer is yes. And there's a concept called LoRA, low rank adaptation. It's basically an idea that we have our original weights, we can quantize it, but when we're training and adding additional weights, what if we can find a lower rank, which could mean a lower dimension, that we can use that as separate that as two, basically the delta W is our added weights. Now we're splitting that, we're decomposing that matrices into two matrices called A and B. So now when we multiply those A and B, we get back to those bigger matrices. It's basically matrix decomposition. And we're finding two smaller matrices to multiply together to get a bigger matrices. Now, if we use this idea, now let's say we have a matrices, the orange one with D by K, and they have let's say they're 1,000 by 1,000, so they're parameters. So let's added parameters like a million parameters. So let's actually decompose this matrices by a lower rank R. Then the delta W becomes matrix A D by R, and the matrix is B R by K. So we can multiply D by R times R by K to get D by K. So basically that's the simple matrices calculation. And therefore that 1 million parameters becomes only 24,000 parameters. So the trainable parameters become only 2.2% or sometimes even 1% of the original weights. So that's kind of a big kind of groundbreaking there. So this also introduces another hyperparameters, which is the rank R we have to select. If we kind of drag this red boxes all the way to the right, we get the full fine tuning, which is a million parameters in our example. But if we find the lower rank R, this rank could be somewhere in the middle or maybe near the origin. We can find a smaller matrices, smaller percentage of trainable weights that could represent intrinsically to the bigger weights, and that's what the paper of LoRa was talking about. The paper of LoRa was talking about there exists a lower rank dimension R that intrinsically can represent the full rank. Therefore, we don't need to fine tune the full size. We just need to find a lower rank R that can be representative, so that we only train a small percentages of the original weights. So now let's put that idea back into our bigger example earlier. So still we have a 7 billion parameter model. Now we've quantized the blue matrices now down to 3.5 gigabytes. And now for the rest of fine tuning, we're only training very small percentage of the original weights, which is the orange boxes on the right side. Now only takes about 1 gigabyte for the gradient and 2 gigabyte for the optimized. This is the rough estimation. So actually now the total memory footprint only takes about 6.5 gigabyte. We can easily fit that into our consumer grade computer. We don't need to buy a $10,000 a data center computer. I can actually do that on my own computer today, like with my own laptop. So with quantization, with LoRa, we can actually, it opens up a lot of possibilities to average users like you and me to be able to customize our large language models, to be able to actually do a lot of things with our large language models. So to do a little bit summary, we talk about today's quantization. It's basically a way to shrink our large language models so it reduces the memory footprint on our GPU. And we'll talk about how quantization is and how it works. And also we'll talk about the idea of LoRa. Basically, is matrices decomposition. We're shrinking our trainable weights to a smaller two matrices and can be multiplied together. Therefore, we only are training small percentages of the original weights. Now we combine those two ideas together, we get a QLoRa, which is quantization plus LoRa, and therefore that opens up a lot more opportunities for many people around the world. So with that, I conclude with my presentation today, and thank you very much for listening. If you have any questions, please feel free to reach out at my email there below, and thank you so much.